Hey everyone, welcome to this explainer. Today we're heading straight into the engineering lab to do something super practical, translating textbook motor physics into real-world performance prediction. If you've ever stared at a motor specification sheet and felt like you were trying to decipher some ancient, forgotten language, well, you are definitely on the right place.
So here's the big question, right? How do we actually predict a motor's behavior before we even flip the switch? As an engineering student, or really any hardware designer, this is literally the ultimate question you face when evaluating parts for a new design. You can't just hook up a power supply, slap on a heavy mechanical load, cross your fingers, and hope the system performs the way you need it to. You need absolute certainty. You need the math. So, let's dive right into it.
Take a look at this Bodine permanent magnet DC motor. It's an absolutely fantastic piece of hardware, the kind of thing you'll find in everything from high-end medical imaging gear to heavy-duty industrial conveyor belts. But to figure out how it's actually going to behave under different physical loads, looking at the shiny metal casing doesn't help us. We've got to unlock its mathematical DNA, and we do that by calculating its core constants.
All right, here's our quick roadmap for today. First, we'll meet the motor constants. Second, we'll define torque and voltage. Third, we're going to decode a Bodine performance graph. Fourth, we'll predict behavior under load. And finally, number 5, we'll engineer some real-world steady states.
Section 1. Meet the motor constants.
To put it simply, instead of treating a motor like this mysterious, magical black box, constants let you calculate exactly how much current it's going to draw, or how fast it will spin under very specific conditions. Think of them as the fixed mathematical bridges connecting the electrical world, your volts and amps, to the mechanical world of spin and twist.
Moving right along to Section 2. Torque and voltage defined. Okay, so on one side of the ring, we have the torque constant, or KT. This little guy is responsible for turning electrical current directly into mechanical torque. Basically, if you shove a certain amount of current into the motor, KT tells you exactly how much rotational grunt you're getting out. On the flip side, we have the voltage constant, or KE, and this does the exact opposite. It turns mechanical speed into generated voltage, what we call back EMF. So as the motor spins, it acts just like a generator, and KE tells you how much voltage it's creating to push back against your power supply.
Now, you might want to grab a screenshot of this cheat sheet. It neatly organizes all the core formulas, including the electrical and mechanical time constants. What's really fascinating here is how it reveals exactly how resistance, inductance, and armature inertia mathematically tie the whole electromechanical system together. For example, just look at the mechanical time constant. It actually relies directly on the product of those torque and voltage constants. It's all connected.
All right, Section 3, Decoding the Bodine Graph.
Check out this standard speed and torque performance graph for a Bodine brushless DC motor. I love this because it brilliantly illustrates how manufacturers basically hand you the answers, hiding them right in plain sight. If you look closely at that red line mapping out the current, you'll see the linear equation is explicitly printed right there on the chart. Y equals 0.1044x plus 0.2522. Believe it or not, that single equation contains the exact key we need to unlock the torque constant.
Let's break down this visual math into 3 super simple steps. Step 1. Identify that linear current equation. Step 2. Isolate the slope of that line, the m variable from algebra class. In our equation, that slope is 0.1044. And step 3. To find the torque constant, or KT, you literally just divide 1 by that slope. Yep, that's it. Just 1 divided by m.
And boom, just like that, we've extracted a torque constant of 9.579 ounce-inches per amp, pulling it straight from the manufacturer's graphical slope. So what does that mean? It means every single amp of current you feed into this specific Bodine motor will reliably churn out 9.579 ounce-inches of torque. Oh, and bonus, once you have KT, you can super easily calculate the voltage constant, KE, because they are directly proportional to each other.
Which brings us to Section 4, Predicting Behavior Under Load. By plugging the constants we just found into these core system equations, we can model pretty much everything. The first equation shows us that the total voltage V equals the voltage drop across the winding resistance, plus the back EMF generated by the spinning motor. The second equation is even simpler. Torque equals the torque constant multiplied by the current. When you use these two together, you can perfectly model the proportional output torque for any given current and figure out the exact voltage you need to hit a specific target speed under a specific load.
But here's the crucial part. Understanding exactly how the motor gets up to that target speed. Because when you apply voltage, the motor doesn't just instantly teleport to full speed, right? It ramps up. This data curve brilliantly shows how that mechanical time constant we talked about earlier dictates the precise chronological curve of the motor, reaching 63.2% of its final steady-state speed.
Let's walk through how this builds into a complete timeline. It's essentially a chronological chain reaction that perfectly demonstrates Faraday's law in action. First up, voltage is applied. Second, since the motor isn't spinning yet, there's zero back EMF, which means a massive rush of current flows in, creating a huge spike in torque. Third, as that massive torque spins the motor faster and faster, the back EMF starts to rise, acting like a brake on all that incoming current. And finally, step 4, the rising back EMF chokes off the current until the internal torque produced exactly matches the external load you're trying to move.
And that leads us perfectly into Section 5, Engineering Real-World Steady States.
Reaching steady state is really the ultimate goal of all these calculations. It's the precise condition where the motor speed is totally flat, neither increasing nor decreasing. It means the battle between the applied voltage pushing power in and the generated back EMF pushing back has found a perfect equilibrium. And that balance is dictated entirely by whatever mechanical load is fighting against it, whether that's the constant air drag on a drone's propellers or the heavy gravity acting on a vehicle pulling up a steep gradient.
Let's look at a practical scenario presented by Professor L. Kanen. Imagine an electric vehicle cruising along at a steady 36 kilometers per hour. We know the applied voltage from the battery is 25 volts, and the measured back EMF is 24 volts. The winding resistance is sitting at 20 milliohms. Now, because we are in a steady state, that tiny 1-volt difference is precisely what's driving the exact amount of current needed to overcome the vehicle's air drag and road friction at that specific speed.
So, I want you to put your engineer hat on for a second. If we suddenly crank that applied voltage up by just 1 volt, making it 26 volts, what would be the new final speed of the vehicle? Well, using the constants we've been discussing, you know exactly how this plays out. That extra volt widens the gap between the applied voltage and the back EMF. That pushes a fresh surge of current into the motor, which our trusty torque constant multiplies into higher mechanical torque. The vehicle accelerates until its speed climbs high enough for the voltage constant to generate a matching higher back EMF, choking the current back down until it settles into a completely new steady-state speed.
Professor Kanen actually has an elegant summary that perfectly encapsulates everything we've unpacked today. He says, so where the load torque is exactly balanced by the torque supplied by the motor, that is when steady state is reached. It's a great reminder of how electrical voltage and mechanical physics are in this constant, ongoing negotiation with each other, strictly following the rules set by the motor's constants. Now that you know how to decode a manufacturer's performance graph, quickly find your KT and KE values, and model these dynamic responses, you've got some serious analytical power at your fingertips. You don't have to guess anymore. You can perfectly match any motor to any system's dynamics before you ever build a single prototype. So I'll leave you with this final question. How are you going to use these constants to predict the behavior of your next engineering design? Thank you so much for joining me on this explainer. Keep calculating, keep designing, and I'll catch you next time.